There are many advanced aspects and features of the BEX software which I've not been able to go through in this series of introductory talks. In this talk I'm just going to focus on one aspect of this. What I've done here is I've loaded a calibration sphere measured on a Taycan Technologies RS6000 air bearing system. You see the data set in front of us. I've got some contour lines fitted here. If we click on the right, the contours are set at 100 contours per millimeter. The measurement area, if we look at the information box on the left now shown, is 101 by 101 data, 40 micron spacing, so the area is 4 millimeters by 4 millimeters as shown in the cross section. I can now use the Z scale zoom on the top here with the pointer just to emphasize the spherical nature of this, and you can see that here, basically expanding the Z axis so that you get a better representation of the surface. Not that necessary here, but it gives you the sense of the sphericity of this calibration artifact. What I'd like to do here is just go to the top left here, edit the data. There's a series of options here, many of which have sub-menus, and many of these are centered around complex measurements of maybe very rough surfaces or surfaces with wear and other features, so that you have the option to work with bad data points that have not been measured, the ability to invert data in the X, Y or Z plane. We have some software here for removing spikes in the data. We can filter the data, and this is three-dimensional filtering using median filters or a three-dimensional Gaussian filter. These two are to do with the mouse button actions, translating and rotation, which we are already doing. Finally, we have the form fitting, which we've seen on a number of occasions as a standard action, is to fit a plane, and we've seen that plane fitted to all data sets in some cases. What I'm going to do here is actually show you another way of doing this, and I'll come back to this in a second. I just click that off. We've seen 2D parameters. We have 3D characterization here, which will lead to a series of S parameters, which will be covered in a much more in-depth presentation to follow. But here you can see I can fit a sphere to the surface, and we have a calibration sphere in the image plane. I can fit mean Z plane polynomial with different degrees of order to the polynomial. I can apply that. I can then select the form, display the form, fixate the data. Many options here, but the simple action, which is the topic of this presentation, is just to simplify that. Let's go back to the infill pane as shown, edit the data, fit the form, fit the sphere, and there very quickly you see a sphere has been fitted to the data. What you see in front of you is the automated residual mapping of the surface with the sphere removed, and you can see that in the title here, where the Chrome test, the sphere has been removed from the data. If you want to know what the radius of the sphere is, that's shown in the bottom left here, and you can see the radius of this particular sphere is 21.960 millimeters. Let's look at the residual error. Bearing in mind this is an air bearing system, so the table is very flat with its motion. Let's do the top down view, zoom in, and we can see a cross section here right through the center of the residual data after the sphere has been removed, so this is nominally a flat surface. And if we now look at the 2D section, we can see that the 2D section here is running between 50 nanometers on the left and between minus 50 and 100, minus 100 nanometers is representing it. If we just look at the 2D parameters, just looking at the PA value for the raw data, you can see that is 47 nanometers. Bearing in mind the resolution of the optical sensor here was 10 nanometers, we're just 5 orders of magnitude above the resolution of the sensor, so this is very good. It's an indication of the noise floor of the system.